Thanks. Hi everyone. I'm happy that so many of you have came here to follow my talk. Today I'm going to show you how to exploit your GPU power with PyCUDA and friends. Someone asked me if the and friends part means OpenCL. Well, we are not looking at OpenCL, but we are looking at a couple of libraries that let you do GPU computing at a higher level than PyCUDA. We will compare OpenCL in a couple of occasions with CUDA and seeing the main difference. During the preparation of this talk, I found a lot of documentation, a lot of material, and I gathered them to this reference website. I also wrote some code that I can't show you today, but you can go on the website and download it. And let's see what are the topics for today. For today, I'm going to talk about what is a GPU and what is GPU computing, a little introduction. Then I will talk about CUDA and how it works. And then we will look about PyCUDA, how you can access to the CUDA NVIDIA C APIs from Python. We will see a short example of how PyCUDA works and what are the main features. And we will talk a little about tasks that run fast on GPU. And finally, I will present you the libraries that I said before for doing GPU computing at an higher level. Let's start with the first topic. And what is a GPU? Well, a GPU is the acronym for Graphic Processing Unit. And they were firstly designed to help the CPU in doing graphic rendering operations. They are found in almost all modern devices and personal computers. Due to the high parallel nature of the graphic rendering operations, they became more and more multi-core processor. They increased the number of their cores to do this operation fast. And if you look at the GPU, you can find some difference with respect to the CPU. The image behind me shows how these two processing units differs by themselves. The CPU try to achieve the best performance relying on a big and fast caching systems, and a complex flow control. While the GPU try to achieve the best arithmetical throughput, relying on a great number of arithmetical and logical units, and try to keep simple the control system and the memory, the caching system. So when the GPUs overcame their limits of doing just graphic rendering operations, this leading to the born of the GPU computing, to the birth of the GPU computing. In GPU computing, the GPU works as a coprocessor for the CPU. And in your application, you can move the tasks that can be executed in parallel to the GPU and achieve and exploit the high multi-core architecture of the GPU to achieve some speed-ups. However, these speed-ups are limited by the Amdahl's law. So GPU computing has more sense if used when your application do a lot of parallel computation. The main time-consuming task of your application is a parallel executable one. Also, in GPU computing, you have to consider some overheads. Overheads that are given by the memory transfer and the communication between the CPU and the GPU. You have to transfer the input data to the GPU and then do the computation on the GPU and then finally transfer back to the CPU the results of your computation. How CUDA is related in this how CUDA is related to this context? CUDA is an NVIDIA technology that lets you do GPU computing. It was released since 2006 and now is widely diffused in high-performance computing environments and also in some end-user softwares. On the NVIDIA.com site, you can find a showcase that lists all the libraries and the software, many of the libraries and many of the software that relies on CUDA to achieve high-speed apps. However, CUDA is not the only technology to do GPU computing. The other most famous alternative is OpenCL. OpenCL is a library that lets you write applications that scale on parallel application that scale on the that scale, and they work on a heterogeneous number of architectures. So it's like you write once and run everywhere. OpenCL is very similar to CUDA. If we talk about the programming model, they are very similar. There are also automatic tools that you can use to translate the CUDA programs to the OpenCL programs and vice versa. I linked one tool on my reference site. And the first question that you may ask is, why using one instead of another? Why using OpenCL instead of CUDA, or CUDA instead of OpenCL, since if we talk about performance, they are almost the same. The main maintainer of the PyCUDA and PyOpenCL bindings has compiled the list when he lists the pros and cons of each technology. It finally says that there are no strong reasons to use one instead of another. In my opinion, there are still some reasons to use CUDA in a production environment. There are a couple of reasons. The first reason is the maturity of CUDA with respect to OpenCL. As I said before, CUDA has been released since 2006 and now is widely used in high-performance computing and is tested on a wide range of software. And OpenCL lacks this maturity. And the second reason is support. Because for the CUDA technology, the support is provided by the NVIDIA. While for OpenCL, every hardware producer must provide its own support to the OpenCL technology. And in many cases, I found that this support is outdated, or maybe is the driver that support OpenCL are still in beta release or does not work very well. So this is why, for a production environment, I'm still looking at CUDA for doing GPU computing. Yeah?
I think there's one other difference, but you might know more than this. Hello. Okay, so there's, I think, another difference. OpenCL running on the Radeon cards, as far as I know, the Radeon cards are faster with integer math. And NVIDIA's GTX cards are faster at floating point, particularly double precision floating point, and I think have better IEEE accuracy as well. So there may be a difference there if you're choosing a card as to whether you go with CUDA and NVIDIA and OpenCL and ATI's cards.
This is about running an OpenCL program. Okay. There are work that I linked on my reference site about the comparison from an OpenCL program that run on the NVIDIA and on the ATI graphic cards. And they show that ATI graphic cards, yes, run faster on some kind of tasks, but many of the programs that run faster than the NVIDIA ones are written not in OpenCL, but in their intermediate language. And the OpenCL program, they are compiled to an intermediate language and then executed by the GPU. You can upload and they are automatically translated and executed on the GPU. The same thing is for the NVIDIA ATI cards, the NVIDIA graphic cards, when you compile to the PTX format. And most of the performance are gained if you write or you modify this intermediate language. Okay. Let's see the next slide. Oh, well, I want to show to you how CUDA programming model works. And, well, host and device are the two keywords that the CUDA programming model used to identify the CPU-related resource and the device-related resource, like threads and memory. CUDA lets you define functions that will be executed on the device instead of the host at the runtime. And these functions are called kernel, and you can decide how many threads will be executing these functions. So you can launch a function on the device and then make it executed by a certain number of threads. Each of these threads has an ID that identify the threads inside an ID. These threads are then divided in blocks. Each thread has an ID, and each block has an ID, and all the blocks form the execution grid. So we have a lot of threads that are executing the same kernel function, and you can fetch the ID by the inside of your kernel to know how in which thread you are, and to fetch the memory and to choose what are the computations that you have to do inside your thread. During their life, threads can access to different memory spaces. The first memory space that the thread can access to is the local memory space. It's a space that isn't accessible by any other threads in the execution grid or in the same block. Second memory space is a per block shared memory space, and it's a space that can be used to share the data, the results of the computations between the threads of the same blocks. You can do communication inside this space. The last space that a thread can access is the global memory space. Each thread of the grid can access this global memory, and this global memory is the only memory space that can be accessed also by the host. So the host put the data in the global memory. Then each thread can fetch the data from the global memory, do their computation using maybe the local memory or the shared memory, and then put the results in the global memory again, and the host can fetch the results back to the CPU. So this is how CUDA programming model works. Since we are at EuroPython, we want to see how to access all this from Python. And one answer is PyCUDA. PyCUDA is a library that lets you access to the NVIDIA CAPIs, let you access to the NVIDIA CUDA technology in a very easy manner. You have a lot of features that make you easy to write programs, to make you easy to write programs that exploit the CUDA technology. It works like a Python library should work, providing you some feature like automatic object cleanup and error checking and translating into exception, so you can just do a simple try catch to handle some error. And also it has a feature that is a killer feature of PyCUDA, and is metaprogramming. With the NVIDIA CAPIs, you can do metaprogramming. While on PyCUDA, you can you can generate your code at the runtime and then compile and upload to the GPU, exploiting this feature. And it's something that you can do with the NVIDIA CAPIs. OpenCL can. And to see how PyCUDA works, I prepared a very simple example, and it's about the sum of two vectors. It's a very simple task, and the classical way to resolve this task is to looping all over the elements of these two vectors and doing the sum, and then put the results in another vector. It's easy. On the GPU, we use a different approach to solving this task. And we have that each thread do just one sum, And we launch end threads to cover all the elements of the array. So when the kernel execution terminates, we have all the results in our destination vector. If you try to write down a program that do this simple task, it may take you some more line of what you are expecting. And this is the difference. Do not try to read this code. We are zooming all the part of this code, and we start from the bottom. There are about the 50% of code less in the left part where there is the NVIDIA CAPI program, and on the right part we have the PyCUDA program. There are 50% less code, but we are zooming the part starting from the top. The first part is in both program is dedicated to the include and the imports. While on the NVIDIA CAPI program, we just need to include the CUDA.h header to write our CUDA programs. In the PyCUDA programs, we have to import some module. The first module that we import is the PyCUDA.autoinit that performs all the operations that are needed to execute some code on your CUDA device. Then we import our PyCUDA driver that contains a lot of functions that are needed to write our program. We have seen them ahead in this presentation. Then we import the source module class. That is the class that will handle our code. We are seeing the next slide how this class works. And finally, we import NumPy. I forgot to say before that PyCUDA is tightly integrated with NumPy. We use NumPy to manage our arrays, our memory, that has to be copied to the GPU, and which we do computation. So we import NumPy to manage our two vectors. In the next slide, we are seeing our kernel. This is the function that will be executed on the device, and it's extremely simple. It do what I've seen before. It just take the thread ID in which we are, and then sum the corresponding two elements of the vector, and put the result in the resulting vector. One beautiful thing of PyCUDA is that this function is exactly the same on the NVIDIA CAPI program and on the PyCUDA program. We just need to wrap this function with the source module class, and this class will automatically compile and upload to the GPU at the runtime. So you can understand how to do metaprogramming. You can basically upload to the GPU, compile and upload any kind of string, any kind of program that you want to generate. In the next slide, I wrote a check error function. This is why every function in the NVIDIA CAPIs returns an error code. This error code has obviously to be checked to make the things work right. And I write a function that do this. PyCUDA does not need this feature, does not use the error checking, because automatically can catch and translate the errors into exception. So we can just handle it with a try catch. In this slide, we are just declaring our arrays. We do a simple malloc on the NVIDIA CAPI program, and we use NumPy for the PyCUDA program. It's quite simple. And in the next slide, we are copying, in the NVIDIA CAPI program, we are copying the contents of our vectors to the GPU using the CUDA malloc function. This is not needed on PyCUDA. You don't need to explicitly move the memory from the host to the device, because we are seeing in the next slide how PyCUDA can do this automatically. We are at the kernel launch. So each of the programs can configure their kernel specifying how many threads per blocks has to be launched, 256, and then specifying also how many blocks you want to be launch. And after the kernel execution on the NVIDIA C API program, we copy back to the host the results. While PyCUDA, as I said before, can handle this automatically. It can handle this by using the driver function, driver out, driver in, which are used to wrap your vector. This function tells which are the arrays that has to be copied to the GPU before the kernel launch, and which are the arrays that has to be copied back to the CPU after the kernel has finished its execution. After that, we have we check our results. We do the same operation on the CPU to see if the things are going right, and we check that the results on the CPU and the GPU are matching. And finally, we free resources, and on the NVIDIA C API program, we have to do the free and the CUDA free operation. While on PyCUDA, you don't need to do this operation because the objects are automatically collected. And this is a simple example of how PyCUDA works. One interesting thing is that if you try to run this example on your GPU, you won't get any speedups. You won't get maybe a little speedup because summing two vectors is a too simple task for a GPU. It's more like moving memory than doing the sum, because you have to move your data from the host to the device, and then each thread have to fetch both the elements of the array, and then he has finally to sum, and then he has to write to the global memory, and then the host have to fetch from the global memory the results back. It's a lot of memory transfer for doing just one sum. So this is why it's not you got not speed up from this operation. Unfortunately, in most real world cases, you have to face some more complex problems about doing just a sum of two vectors. This problem that I see now is about arithmetical intensity. Arithmetical intensity is when you have a few arithmetical operations and a lot of memory transfers. It's not good for GPU because you are limited by the bandwidth of the memory, and you can't exploit your GPU power, your GPU arithmetical throughput. Arithmetical intensity. I was said before, in real-world tasks, you have to write some more complex program, usually. And it may be easy to write a kernel that do all this, your computation, your task, that solve your task, and do the right things. But it may be harder to write a kernel that run fast, that give you some speedups. This is why writing a good kernel is a matter of that group many topics. The first thing that you have to know to write a good kernel is the CUDA programming model. And I just do a little brief, but in details I skipped many details. And you have to know how to work the CUDA programming model. You have to know how works the underlying architecture. And you have to know how the CUDA programming model is mapped on the architecture. These is our basic things you have to know to do a good work of the optimization to write a good kernel. So you can first, if you have a task to resolve, you can start writing the first kernel you have in mind. And if you know all these things that I said, you can just modify your code step by step to achieve some speedups. And a good work of this kind is done by Mark Harris. Mark Harris is a cool guy that works at NVIDIA, and it made, in my opinion, one of the most beautiful work of CUDA optimization. It shows how you can take a reduction operation. You make, you know what are reductions, and it starts from a simple kernel, from the first kernel he has in mind, and then he starts, then he step by step modify the code to adapt it to the underlying architecture. It shows what he modify and how and why he modify the things, and it finally get 30 times speedups from the with respect to the original kernel that he wrote. And I linked his work on my website. And if you are planning to start using CUDA, to start learning CUDA, I suggest you to look at this example, because it's a very clarifying example about how you can write good kernel. In the end, before I wanted to show you a couple of libraries that let you do GPU computing more easily than knowing all this stuff that I listed. The first library that I want to show to you is also the most exciting in my opinion, and is called Copperhead. Copperhead is a library that lets you do GPU computing using just simple Python syntax. You don't have to know other languages. And let's see an example. Okay, doing GPU computing with Copperhead is as simple as you have to just import the names of the Copperhead module, and then we can define our function. I defined a simple AX plus Y function, and I define this function using a standard list comprehension syntax, using standard zip operator, that is an operator that is overwritten by the name that I imported the Copperhead module from the Copperhead module. And then I can define this function, and I can declare vectors as a standard Python lists, and then I call the AX plus Y function. This function will be automatically executed on the GPU instead of the host. This magic is done just by the decorator at CU that we see above the function. And this decorator tells Copperhead that the function has to be translated to a CUDA kernel, and then it compile and upload to the GPU, and then it executes on the device without that you don't need to know what is behind this. But let's see some details about Copperhead. Well, as I said before, Copperhead can works with just the Python syntax, a subset of the Python syntax. You can use not all the function of Python, obviously, but you can use lambda, you can use map, you can use zip, you can use a lot of functions that Copperhead has overwritten, and to write it and you define your function that will be executed on the GPU. It actually has some limitations. You can work on various kind of array. You can work on lists. You can work on list of lists. You can list of tuples, but you can't work on array of classes and metaclasses. Also, when you are defining your function, you have to adopt a strong typing policy, so your function can return values like 1, 0, true or false, but not 1 or false. You can do this. This strong typing policy is needed to achieve the best performance when you run a Copperhead program. It's tightly integrated with NumPy. Okay, so we can rewrite the previous example, just changing these lines using an NumPy, and it works. You don't need to modify. If you want to use CopperEd, you don't need to modify or rewrite your programs to make it work with CopperEd. And it also offers an easy switching between CPU and GPU with the construct with. With the construct with, you can say where your function will be executed. Since we are using standard Python syntax, we can execute the function both on the GPU or the CPU, and it works both hosted device. And you just have to use the construct with to specify where the places the execution is. Mr. President.
So one of the problems that I've faced using CUDA in the past is not knowing when to put things onto the CUDA card or when to keep them on the CPU.
Can you repeat the question,
sure.
Please?
So I have an array. I want to multiply it.
Yes.
Do I do it on the CPU, the 3-year-old GPU, or the 6-month-old big GPU on my other computer? I have to think about the task. And the same here. Do I execute on the CPU or the GPU? Which is faster? In Copperhead, are they talking about deciding for you?
Actually, CopperEd works that... no. Actually, no. Because CopperEd is a developing project. There is a very good guy, Brian Catanzaro, that is the maintainer of this project. He published I linked on my reference site some documentation that he wrote about CopperEd. And, well, he said that there is a developing project, that there are some, he is mainly focused on another kind of task. He's trying to bring data parallelism to Python, but trying to implement the core of CopperEd in other languages instead of using CUDA, because CopperEd, I will see, is detached from CUDA, is not strictly bound to CUDA. And no, he is not thinking to this kind of optimization, and also you, when you use the construct with, you cannot. You have that these two vectors are also stored on the host or device memory, because if you executing your function at the device memory, you have also the vectors are stored on the device memory, and you cannot mix this. You cannot do with places here and your XP, and then you do a with place your GPU with the same vectors. Maybe in the future they will support this kind of optimization and row profiling to see what are the best choice. Okay. And well, next slide, I want to list some cons of this library. Well, the first cons is about the lack of an extensive documentation. On the main page of the project, you can find some documentation about CopperEd, but there is not too much to read. It's a developing project, so it's lacks from extensive documentation. Yes. As I said before to Ian, CopperEd is a project that trying to support other platforms than CUDA, because CopperEd is a project that aims to bring data parallelism to Python, and it's not strictly related to CUDA. Maybe the next backend will be OpenCL, maybe. My guess is. And as I used this library for a little time, And I wrote some example. There is also an example that I write and I put on my reference site about image fading, a simple example. And my opinion, and also the author opinion, is that this library is not ready for a production environment. As I said before, has some lacks of documentation, and it needs some adjustment. This is why Copperhead has a strong typing policy. So he has a strong type inference system that it doesn't understand always what you are trying to do. If it doesn't understand what you're trying to do, usually it means something like some type inference exception or this sort of things. And you have to modify your code to achieve to run your function. So there are still some adjustment that has to be made to this library. The second library that I want to show to you is Theano. Theano is a library that lets you define mathematical expression, and it compiles them to achieve some speed up. It's offer transparent GPU computing. But let's see how this library works before seeing the details. I copied the example that I did before for Copperhead, and it's the same AEX-PY. But since Theano is a math expression compiler, we have to declare which are the arguments that the function takes as input. So we declare A, that is a scalar, and then X and Y, that are the two vectors. And then we define our operation. And this line, this AEX-PY equal function, this line just compile your expression and optimize your expression for executing. And you can, after define your vector with the standard Python list, as we've seen before, and finally you can call your function. If you look at this code, you can't find any reference to GPU programming because, as I said, Theano offers you transparent GPU computing. So how do you run this code on your GPU? Just simply setting an environment variable. You can set the Theano flags variable of your environment, setting device equal to GPU. And your program will be automatically executed on your GPU. The function will compile code that will be executed on the GPU. Some other details of this library are that it's integrated with NumPy. So as we've seen before, we can substitute the lists with the NumPy array. And things in which differs from Copperhead is that it has an exhaustive documentation on the homepage project. There are a lot of examples, simple example and more complex example. And it's ready for the production environment. It has a BSD license. It has an active community of developers and users. It has a good bug tracking system. Some cons of this library are that there is no full performance portability. Since if you want to write a function, a program that runs fast both on GPU and CPU, you have to use some special function to say which are the variables that has to be copied to the GPU and the variables that can be left on the GPU. Otherwise, you are encountering some performance decreasing given by the massive memory transfers that Theano do. And also, you have that not all the function of the library run faster on the GPU. This is why Theano was mainly designed to write some support vector machine learning algorithms. So it's very good at running linear algebra programs, linear algebra operation, and they all run fast. But for this presentation, I write an example about the convolution, and I was surprised that this convolution was faster on the CPU than the GPU. Maybe I was wrong in writing something, but this is my first impression. Well, I'm almost finished. I want to just do a little summary of what we have seen today. We have seen what is a GPU and what is GPU computer paradigm, how GPU computing works in your application. And we have seen what is CUDA and how CUDA programming model works, a little brief. The details are obviously available online. I suggest you to read the CUDA, the NVIDIA C programming guide. It's a very good introductory guide if you are interested in these topics. And we have seen what is PyCUDA and a little example of how PyCUDA works, what are the advantages in using PyCUDA instead of CUDA. And we have just do a little brief of what are the things that are important to write a good kernel, a fast kernel. And finally, we have seen two libraries that let you do easy GPU computing without knowing all the details of the GPU computing. Oh, so that's all. Thanks. Thanks. Yes.
Just wondering if there is any research or somewhere on the web where there is some metrics about...
Excuse me, can you repeat?
Yeah. I'm just wondering, basically, the choice a developer has to do when thinking about CUDA is about the overhead. And is there some research or somewhere where it said that under, I don't know, 100 operation, 100 operation, like, I don't know, 100 plus, 100 multiply with a scoring, basically, that you can go to PyCUDA or you don't. Is there somewhere this kind of data? Because we can't all of us experiment in each of us in our corner, but it looks like the data that's missing is that.
Yes, PyCUDA has a feature like this that it's not like that it tests all when the operation goes faster, but it tests the kernel launch configuration. It's a very important thing when you do GPU programming to rightly configure your kernel. The ratio between the threads per blocks and blocks can change a lot your speed up, your performance. So PyCUDA has some function that like you remember the source module class? Well, it has some classes like this that can you specify just the kernel code without any reference to the thread index that you have to fetch in the source module class, and it automatically choose the configuration of your kernel. And it's a good thing because otherwise you have to test on every time, and when you are in production environment, maybe you don't know which on which your program will be run. Maybe you are writing a program that uses CUDA, but you don't know if your user are running a last generation Fermi the CUDA device or an old one. Oh, I didn't. I wanted to show you all the feature, but it would require a deep knowledge of how the CUDA programming model works, and also how the device, which is the device model of the CUDA hardware architecture. However, you can send me an email. I can answer to your question if you want.
Hi. So I can see how CUDA could help me to do some linear computing on vectors, but does the library also provide any high-level functions to maybe work on, let's say, geographical data, or maybe building indexes, or I don't know, whatever?
There are some high-level functions, but they are especially about linear algebra. I didn't find anything about the geographical library for CUDA. But if your problems are related, I don't know what kind of problem there are in geographical problems. But if you use linear algebra, or if you use something that is more mathematical, you can find a lot of library. The Theano is one good library. There are also some NVIDIA wrote also some linear algebra functions. They call them. I forgot the name. We can check online maybe after. And you can use this function to make to solving your linear algebra problems. If you have a complex task or a custom task, you usually it's better if you write your own kernel. You can write for complex tasks. I use CUDA in my work for a couple of tasks, and also I have always to write my own kernel. This is why it's very important to know how the architecture works, how the CUDA programming model is mapped.
I have actually two. The first one is maybe I'm missing somewhat, but isn't it the most basic precondition for doing this stuff that the problem you are trying to solve can be naturally decomposed into smaller subtasks?
Yes, this is the you asking me. I don't understand the question exactly.
The question is, you have presented some problems, simple problems. All of them are list comprehensions, map expressions, stuff which can be naturally decomposed into smaller steps. Yes. If you have a pile of code which is sequentially in nature, highly interdependent,
okay.
What are you doing then?
Well, there are a good question. It's a more technical question. If you have a lot of serial executable code that you can parallelize, you can try to change your program. Maybe if you are doing, you can use CUDA to just solve many of these problems in parallel. Just one thread can solve one of your problems, or maybe one block can solve one of your problems, and then from the host you can solve a bunch, a group of these problems. It's high problem dependent. This finding a solution.
Algorithmic problem, I think, or?
Yes. It's more a kind of finding the right algorithm and the right structure to model your problem, and then you can. CUDA programming is not a so simple task. Many people say, you use CUDA, you get 50 times speed ups. It's not so easy. It's easy in a lot of tasks, linear algebra and high parallelizable tasks. But writing a custom algorithm is something more complex.
All right. Second one is, which is your main platform for doing this stuff, and how is the Linux experience?
Oh, well, I I switched to a Mac just some month ago. So I before used always Linux. And with Linux, well, it works. I tried PyCUDA and CUDA on Linux platform, on Mac platform, and I don't not try Windows. I hate Windows. And it works well. It works quite well. I found just a little difficult to install Copperhead because it has some dependencies. It's a developing project, so you have to download your dependencies. There is not. You have to check out the source code from the repositories and compile. You have to do this kind of stuff. Not too much difficult, but it's not immediate as just installing PyCUDA. If you want to install PyCUDA, you just have to type easy install PyCUDA, and you got PyCUDA. It's very simple. After you have the installed your NVIDIA SDK toolkit that you can download for free from the NVIDIA. Oh, yeah.
So just an announce, first of all, I'm running the high-performance Python tutorial this afternoon, and in that we're going to be looking a lot of compiler stuff on the CPU and also having a look at PyCUDA at the end. There's going to be an awful lot of questions that come out of that 4-hour session, so I've arranged a birds of a feather meeting tomorrow morning, 10:30 to 11 a.m. in the open space outside the big tent. So if you're interested in high-performance computing of any sort or artificial intelligence, please come along 10:30 and the coffee break to the open space. And I've got a practical answer or practical bit of experience for the chap who asked about which array sizes make the best performance on CUDA. The short answer is I don't think there is a clear answer. It all depends on which hardware you're running, be it CPU and GPU. I've used it over 2 years. I've gone down to writing C in CUDA. And you can get great performance benefits. I've got 160 times speed up versus an OpenMP optimized CPU quad-core solution. But that took about 6 months worth of work. Now that's the downside. The upside is that NVIDIA are saying that we can buy 1,000 cores on a card for £400 at the moment running on a 750-watt power supply. What they want within the next 4 years is 20,000 cores, so that's ahead of Moore's law. So if you start to use CUDA or OpenCL, any of the massively parallel techniques now, you're going to end up being ahead of the curve a couple of years down the line when many more problems will just run faster naturally, really easily on a GPU. Or a couple of GPUs, or a cluster of GPUs. So if you're at all interested in this area for the next couple of years, it's definitely worth getting a card, even a slow, cheap card, and just experimenting so that you're aware of the language and the different way you have to think about the problem. And then you just have to start doing performance benchmarks and see when it really works out for you.
Any more questions?
You show a simple example with two vectors, which are, one-dimensional.
Yes, very simple example.
But what about going to higher dimensions, so matrix or three-dimensional arrays? So is everything much more complicated? You can easily use this?
No, it's not much more complicated. There are, as I said before, there are a lot of libraries that do these simple linear algebra tasks in a very efficient way. So if you want to do some linear algebra operation, you don't write your own kernel, you just use some libraries. Switching to other dimension is really not a problem. Since I don't present the details of the CUDA programming model, but every thread can have an ID that can be up to the three-dimensional array of integers. So you can shape your threads to get to scale on more dimension. Also, the blocks can have a two-dimensional array, so you can easily do things like this yes. That is not too difficult.
So in the back of my mind, I've got this idea that there's a library of CUDA kernels that maybe NVIDIA supply. Is that possible to access through the PyCUDA interface?
Well, I don't understand the question.
So for kind of common tasks like FFT or something that you really want to engineer your kernel for, I've got this kind of feeling that NVIDIA provide a library of them.
Valentino, can I help you?
Te lo dico in italiano. Per task...
Sorry, it's not your problem, it's my fault.
Per task comuni tipo trasformate di Fourier, cose così.
Yes, there are a lot of libraries for doing this kind of signal processing. There are NVIDIA provides its own library about doing fast Fourier transformation. And also, I'd like to, for this talk, I wanted to implement the R wavelet function, you know. Yes, the R wavelet compression algorithm for an image, but I don't have enough time to do this. But it's not too difficult to use to implement something like this, and there are also some libraries. I suggest to you to look on the to go in to see on the NVIDIA site what are the libraries that are officially supported by the NVIDIA, and you will find surely something about signal processing and something more mathematical, something more formal in this way. There is some libraries have bindings for Python. Someone I don't know. I didn't try the library for doing Fourier transformation, but I think that maybe there are bindings for this library. Well, maybe.
Just a notice, GPUs are changing because they are the modern GPUs, such as the NVIDIA's Fermi or the latest announced AMD GPU, are much more similar to CPU. They already can do class calling methods, calling functions with recursion and so on. The latest AMD GPU is able to do quite much more complex things. So you are not limited to the linear algebra right now with the modern GPUs, and it's for the better on the future. And the only thing that we need to care about GPU computing is about the round trip between the CPU and the GPU. Because the PCI Express is a good point-to-point connection, but it's slow. Something can change when we have a CPU and GPU on the same die. If they are on the same die, such as the AMD Fusion project, we don't have a slow bus in the middle. So the CPU can send data on the GPU, which is on its side. So it will be changing a lot the GPU computing in the next years.
One last thing. I forgot to say that I wrote some code that I put on the reference site. And this is, I want to show you as an example of how you can simply translate a program from the NVIDIA C APIs to PyCUDA. This is an example that the NVIDIA provide. Yes, that the NVIDIA provide with his SDK. I just translated this example to PyCUDA to do the same exactly thing, since the kernel is always the same. And this is a Sobel filter operation. This is the convolution that I tried with Teano, and it was slow. And it can do well. You can see the difference, but inside this program there are 3 kernels that do the same operation using some different feature of the CUDA programming model. I didn't talk about texture, about OpenGL integration, interoperation. There are a lot of features that I can't, that I would like to present to you, but there is not time. But you can find this script. This example is quite complete for the CUDA feature that you can use. So you can just go on the reference site and download it if you like. Okay.
Any more questions? Is probably the last question.
So I saw in the code that you have two, and you can specify the number of blocks and of threads.
Yes.
And is it bound to your architecture that you have? So if someone else uses it on another chipset, does it affect performance?
For this example, I used a quite low number, so it will run on every architecture. But yes, it's hardware dependent. You have some cards that supports a greater number of threads per blocks, and you have architecture that supports that can run more blocks than others. But however, for this simple example, I tried it on my Mac and on a Linux personal computer, and it works quite well. I tried it on also on some different GPUs. At work, we have at my job we have a GTX 260 for doing some tries. And on my Mac, there is a mobile version of the NVIDIA GPU, and on my other workstation, I got an integrated chipset of the NVIDIA, an old one, and it runs on every platform that I tried.
Thanks.
You're welcome.
Any more questions? Actually, that was the last one.